everyone. I just wanted to do a really quick, hopefully somewhat quick video, a couple of videos about a little different this time. I want to walk through what's in the reading with you and kind of explain a little bit, connect what you've read already to what we did in class today, and then kind of go through the assigned reading, and that way maybe you can follow along. It is a little abstract just to read about it, and I didn't want to just make a separate video completely disconnected from it. So here's our chapter 10, which is where we're starting with rotational variables, and the reading that was due today was sections 10.1 and 10.3. We skipped 10.2. I'm going to show you why in a second. So the beginning, all it really does is kind of set up this idea of rotation, talks about the idea of, let me put this over here so you could see, theta, S equals R theta, the whole idea of rotating and what angular position, angular velocity, you could see, right up here, omega is d theta dt, and then it gets into alpha being d omega dt. So all the things we did in class today with the angular variables, and then it does some nice examples over here that you don't really need to go through at some point. They're very similar to what we did in class. What I wanted to point out to you is what's at the top of page 264. It actually goes through that little calculus trick I showed you. It takes an angular acceleration. We know that we can get from theta to omega and omega to alpha by differentiating. It shows you how to start with alpha, work your way backwards by integrating with that little trick. It actually does it in the way with the constant, like we brought up in class, that alternate way. So you can either integrate between two distinct times, or you can just say, there's Yogi, he just joined us. Or you could say, it's a constant and figure out the variables. So if you want to see like another approach to how to get from alpha to omega and then omega to theta, you could see how they do the same thing. They do that little d omega dt and they flip it to the other side and they hit an integral on both sides and go through that process. So I just wanted to point out that it's in there if you felt like you needed to see that one more time. Okay, we move on. Section 10.2 we skipped. The reason we skipped it is it was where we defined the big five for rotational variables. So there's no need to go through that unless you want a full review. But I did want to point out at the bottom of page 266 is a really handy little table that has all the linear equations. It has like when they're useful, what variables they have and don't have, and then it has the corresponding angular equation. So it's just a handy table of everything all together. And then the book goes on in 10.2, does some more examples, and then really the 10.3 just relates linear to angular variables, so S equals R theta, V equals R omega, and A equals R alpha. So that's all said and done. You'll have practice with that all in the assignment tonight. What I really wanted to focus on is sections 10.4 and 10.5, which is new. We didn't talk about this in class except very briefly at the end, and I want you to try to pick some of this up through the reading in this video. So let's take a look. So now we know a few things, right? We have some angular variables. We know how to describe them. We know how to calculate them. We know how to do calculus with them. So we have a good handle on how to describe rotation. And now we want to be able to ask a very simple question. How do I calculate the kinetic energy of a rotating object? That's what we want to do. We know how to calculate it of a normal object, right? It's 1/2 mv squared. And we might have some ideas like, well, v is kind of omega-ish, right? But like, is it just 1/2 m omega squared? Like, is that how it works? Is it just 1/2 m r squared omega squared if I put in v equals r omega? Not quite. It depends on a little bit more. If you recall, when I had you rotating things around different axes, they feel different. And so the mass distribution is going to affect the kinetic energy of an object, and we have to figure out how that comes into play. So the thing about the kinetic energy of rotation, I want to walk you through basically the little derivation that's on pages, starts on page 272, because it's very worthwhile to go through. First thing they do is they kind of assume, and they don't draw a picture here, which I kind of wish they did. Let's just sort of imagine that you have some random object and it has all these little pieces of mass, and they're really all little dm's, but we can call them like mi. And let's say we're rotating about some random point P, well, like over there. Each one of these has an Ri associated with it. So each has a distance from the rotation, and each one of those is basically going in its own little private circle. right? This one is going in this circle. This one's going in its own little, circle about of that radius. They each have their own little circle as they rotate around point P. And so we have all these little masses. They each have their own little rotational circle. They each have their own little velocity, VI. And so it seems like if I just did 1/2 mi VI squared and then added it up for all the little m's, I would get a measure of the kinetic energy. And in fact, that's true. If I did 1/2 mi V1 squared plus 1/2 m2 V2 squared and added up every single little piece of mass, I would get the total kinetic energy. And that's represented here by this, I'm going to refocus this, by this 1/2 mi VI squared right there. The problem is every single mass has its own velocity. Remember in class we talked about the fact that if you're like on the inner part of the circle and the outer part of the circle, you actually have different velocities. If you rotate together, the one on the outside is actually going faster. So we could say, well, is there a quantity about rotation that is the same for every mass in that object? And the answer is yes, it's omega. Even though each one of these little masses is at a different location, they're all rotating with the same angular velocity. They're making the same number of revolutions in every second. Some are traveling faster in order to do that. Others are traveling at slower velocities, but they all have the same angular velocity. So what Halliday goes ahead and does at this point is he says, let's take that VI and let's represent it by Ri times omega. Because I know the speed is only going to depend on how far they are from the axis, and everybody has the same omega. And since that's v squared, that's going to be Ri omega squared in that little summation, which is what he does right over here. And then he expands it out and recognizes that the omega is actually not changing, right? It's the same for everything, so it's just a constant. You could pull that out in front, and it's this sum of mi/ri squared that is the only thing that you're really summing over, that you're left with. So this quantity here, he actually calls the rotational inertia or the moment of inertia, and it's symbolized by the letter I for inertia, so it makes sense. But let's think about what that really is. It's kind of a measure of each bit of mass in the object weighted by how far away from the axis it is. But the Ri squared is actually really helpful too, because whether you have like a positive or a negative value for your distance from the rotation axis doesn't matter, because it's going to square. So it's truly just a position. It's like just a how far away kind of thing. It's a scalar quantity. I have the Ri squareds, I have the mi's. I do like, okay, this mi Ri squared, this mi Ri squared, this mi Ri squared. And the masses that are at a further distance from the axis of rotation are going to be weighted more important in that than the ones that are closer to the axis of rotation. And we saw that, right? We saw that when I twisted the little pencil this way, it was very easy to rotate because all the masses are pretty close to that central axis of rotation. The Ri's are all very small. When I rotate it this way, when I shake it this way, I feel the pencil more, like I feel its sluggishness more. That's because I have mass that's way out here, far away with bigger R's, and it's weighted in this rotational inertia. So this is really that thing we were looking for. It's kind of like mass, but it's mass and also where the mass is. And it's a very important quantity in physics when you're dealing with the rotation of objects. So he comes down here and he writes it out. Moment of inertia is just for an object the sum over all the i's of mi and Ri squared. You think about, how do I calculate this? Well, it's pretty easy. If I have like a thing with two things on the end, I can just do the mi's and the Ri squareds and add them up. But if I have like a continuous object like this, I can't just like add up all these little pieces of mass. And you know that when I'm like adding up all of these little pieces of something and then adding them up all over a whole object, you know that's going to turn into an integral at some point, and that's how we would calculate this. Now the good news is that we're not going to spend a lot of time. Well, it's not actually the good news, because it's really fun to do, and I'm going to do a short little video showing you how to do it. But in the AP curriculum, we don't spend a ton of time calculating moments of inertia of objects. We'll do a little practice, but it's not a huge part of what we spend our time on in this in this section. It's not really too much on the test except for like a simple linear rod, but we'll do a couple of more interesting shapes just to understand it. But you turn the page and you get to this, which is like one of the most useful things, which is someone actually calculated the moment of inertia using calculus for all these different common shapes around common rotational axes. So like a ring rotating around an axis through the center has a moment of inertia of m times r squared. If the ring has a little thickness, it's slightly different because it involves both the inner and the outer radius. If it's a cylinder or even a disc, because it turns out to be independent of the length, so it can be as short or as long as you want, so it can be a spinning disc, it's given by 1/2 mr squared. If I take that same disc but I rotate it around an axis this way instead of an axis along the center, it's slightly different. It's this more complicated thing. If the disc has no appreciable radius and it's really a thin rod, it turns to that, which is similar to that but different. You can see how maybe those are related. A sphere through any axis through the diameter is given by that. A shell is given by that. A ring rotated like a hula hoop, not hula hoop style, but flipped over style, is a slightly different because it's a different rotational axis. So the masses are different. They're located differently from that rotational axis than they are around that rotational axis. And so, and then we have over here like a slab, and that slab is rotating, spinning a book around this way, and that has a moment of inertia. So like these are all known, and we know what they are, so we can look them up and use them, and we'll learn one more powerful tool for when they're not exactly that, but pretty close. So when calculating the moment of inertia, so now we have this I, and so what's really important is if you come back to this expression for kinetic energy, because now it's 1/2 I omega squared, which is exactly what we were looking for. We were looking for an analog to 1/2 mv squared. So K is 1/2 mv squared for a translational object moving with velocity v, but if it's rotating about an axis, and it could be doing both, you could suddenly translating and rotating, it has a kinetic energy of 1/2 I omega squared, where I is kind of like the mass, but it has a little bit more to do with how the mass is distributed, and omega is kind of like the velocity, but an angular analog to it. And the units, you can see, if you work out the units here and here, still come out to joules, so everything works out great. All right. So now let's move on over to here. Let's say I'm back, actually, let's go back to this picture. Let's say I'm back in this picture, and I really don't have MIs and RIs. I have this little mass dm, and it's at a distance r. And then I want to integrate over the entire mass of the object, right? I know the integral of dm is just the m, is just the mass. The integral of r dm is the center of mass coordinates, right? Divided by the total mass of the system, but essentially the center of mass coordinates. R squared dm is going to be the moment of inertia. And so it's the same thing. I would just do the integral. Instead of a sum of mi's and ri's, I would do the integral of r squared, where r is the distance to that particular dm. And we'd be able to relate these so that we can actually get an integrable function like we did for center of mass, and I'll do that in another video so you can see how it works out. So you have r squared dm, then you integrate over the whole mass of the object. Conceptually, that would give you the moment of inertia. Okay, but like I said, most of the time we'll be either dealing with discrete masses or looking them up, but the idea is right there. Okay, last thing is this idea, right? Actually, I'm going back. Sorry, so for all the flipping, but there's a lot of flipping. If I come back here, right under here is this little seemingly innocuous thing called the parallel axis theorem. And when you read this, hopefully this makes sense now. It kind of goes into the details of what we we're just talking about. This could get pretty confusing, especially because people don't always bother to stop and think what we mean by parallel axis. And why is the word parallel? And they just think parallel axis theorem and start adding things together and figuring stuff out. You got to really think about what that means. What it means is, if I know, let's say I already know the moment of inertia of an object about the center of mass. So I know if I have a rotation axis that passes through the center of mass of the object. Okay, so picture that. I know the center of mass of the object. I have a rotation axis that passes through that point. Okay. And then I have another axis that's not passing through the center of mass, but that's parallel to the one that is. So they can't be like askew with relative, they have to be parallel. And I want to rotate instead around that axis. There's a trick for how I can say, well, if I know this one through the center of mass, I just have to do this little thing to get the moment of inertia about any parallel axis. It's kind of like translating the moment of inertia over. So for example, if I know the moment of inertia for this pencil, it's so hard to like turn on this. If I know the moment of inertia for this pencil around its center of mass, but instead I want to rotate it around like this random spot over here. So I want to like spin it around like that instead. There's an easy way for me to get there. In fact, this is actually one of your homework assignments, is to take a meter stick and figure out the moment of inertia at the if you were pivoting it around the 20 centimeter mark, which is not at the center of mass. So it's a pretty cute little trick, and it's super useful because a lot of times you're just shifting over your rotation axis. The way you do it is the I about any parallel axis to the center of mass is the I at the center of mass, if you're rotating it in axis through the center of mass, plus mh squared, where m is the mass of the object and h is the distance between those two parallel axes. So like if I had a thing here and my axis was at the 50 centimeter mark and I wanted to rotate it around this 20 centimeter mark, the parallel axis would be 30 centimeters. That's like what I would shift it by, that squared. So it's as simple as that. Taking a number that I have for here, knowing I want to shift it over by some amount h, squaring h, multiplying by the mass, and boom, that's my new center of mass. There's a little proof down here I want to just run through with you. Sorry I wrote all over the book, but I want to just go through this because it's actually kind of an elegant little proof. Here's the picture that we're talking about. So here's this random irregular object, which likely I don't know its moment of inertia around an axis through the center of mass. But it's there, and I'd probably have to do some work to calculate that. But if I do all the work to calculate that, now here my axis is going through the center of mass perpendicular to the paper, so you could picture this object like rotating around the center of mass there. I do all this work to calculate the rotational inertia through the center of mass of this object. And then I want to rotate it now about this point, which is parallel to that point. I've just shifted my pencil over, but it's a whole new point. So what I would do is I'd take the I at the center of mass, I'd add mh squared, where h is the distance here, and that's my new moment of inertia. The way they prove it in this, which is kind of neat, is you kind of look at h over here. It's the distance between the two axes, which are 3D, like this, like pointing into the page next to each other. We call this A and this B the location of P relative to the center of mass, which is at 0, 0. And I'm going to put that in here. The center of mass is at 0, 0. And then my little dm is all the way up here, a distance r from point P. So if I really wanted to calculate this out, using the definition of, relative to point P, I would do an r to dm, and I would integrate r squared dm over this entire object relative to point P, which is what this represents. But now we can note that r is just this squared plus this squared. And if the dm is a distance x and y away from the original axis, and the point P is a distance a and b away from the original axis, then this little triangle is going to be y minus b and x minus a. You can convince yourself of that because this is x, this is a, so this is x minus a. And so I can represent the r squared in the r squared dm as x minus a squared plus y minus b squared, which is what they did here. And then you expand it all out and do all the unfoil or foil or unfurl it or whatever that is, right? And I get an x squared plus y squared dm term. Well, let's think about that. X squared plus y squared is just this distance. That's just the r squared dm around the original center of mass. So this first term here is just the original I center of mass. This last term, the a squared plus b squared dm, that's, if we just think about what a squared plus b squared is, this a squared plus b squared, a squared plus b squared is h squared. And that's a constant. So a squared plus b squared is just h squared. H squared dm is just m, the total mass, times h squared, because h is just a fixed distance between these two axes. It's not something that changes as I go to different masses. So this is just mh squared. And that's the parallel axis theorem. I equals I center of mass plus mh squared. But we've got to prove that this stuff is 0. But let's think about what this is. Remember, integral x dm is just it's like integral x dm divided by the mass, which wouldn't matter in this case, is just the coordinate of your x coordinate of your center of mass. And y dm is the y coordinate of your center of mass if we had divided by the mass. But remember, the coordinates of our center of mass are 0, 0. So it doesn't matter. These terms are both 0. And so there's your proof of the parallel axis theorem. And so the way you use this is you're like, all right, I want to take this rod, which has a moment of inertia of 1/12 ml squared around the center. I want to rotate it some distance, like 10 centimeters off the center. So like I do that. So I would say it's the original moment of inertia, 1/2 ml squared plus mh squared, where h is that distance, and I have the new moment of inertia. And then if I was told it was rotating with an angular velocity omega, I would calculate the kinetic energy as 1/2 I omega squared. So that's it. And like we're going to learn other things too. In your homework, you have a problem that's like this. It has two masses hanging from a pulley, and you're told that the pulley is rotating with an angular velocity omega. And it's a disk about the center. So if it's a disk about the center, you know its moment of inertia. You could figure that out and calculate its rotational kinetic energy. And then you can figure out the velocities of these by knowing that v equals r omega, and you'll know the radius of the pulley. So you can actually work through and get the kinetic energy for real of an Atwood machine at a certain omega. And so that's I think that's your last problem. It'll be fun. All right, that's it. I'm sorry this was a long video, but it kind of covered everything. And hopefully you could sort of just read along with it, and then you don't have to go back and do all the reading. Okay, see you later. Bye.